All right, so we're just working on this problem here. So what do we got? We've got a tank, 22-foot radius or diameter, is that right? And then 16-foot height. And then the weight is 400,000. Okay, so that's what we got. Now, one thing to remember on this stuff is round things you usually spec out by diameter, but you want radius to find the area. So that's the first thing that you do. Now, I just handed out the formula sheet, so keep in mind that you'll have that, whenever you need it. You could use it for homework, of course. I'll give that to you when you take a test as well. So, so just be aware of that. So I've got pi on there if you ever need it. I've got a few things on there. Just have a look at it and, know what's on there. All right, so the deal on this would be, the first thing I do would be to find the area. So that's 380 square feet, roughly, 380.1 if you want to get more accurate, whatever. And then I would take that times the depth, and that'll get me the volume. Now what I'm doing here, see, I've got this number in my calculator now, so I just leave it in the calculator. And then I just go times 16, and that'll get me 6,082 cubic feet. And then I'll take the weight of whatever this stuff is, and I'll divide it by the 6,082 cubic feet. So I'll go ahead and do that. And that's 65.77. That's pounds per cubic foot. So that's what we call the density. And then we can take that and divide it by the standard density of water, which is 62.4. That's on your formula sheet as well. And that gets you the specific gravity. Now that's a unitless number, okay? It's about 1.05. It's just a ratio of whatever you've got. If it's a liquid or a solid, usually you compare it to water. Okay. So we doing okay with that? Do we got any questions with that? All right. So that's some of the basics, of what we've been doing here. It's just that idea there. That's kind of the starting point of hydraulics. So we good? Okay, now we got a few other things that we look at here. One of them is viscosity. The official definition of viscosity is resistance to shear stress, okay? I think maybe a more common sense definition is how sticky a fluid is. Honey has a high viscosity. It doesn't flow as quickly as water does, okay? And so we use what's called dynamic, which is absolute viscosity, okay? And there's ways of testing this. They put a fluid between two plates and they see how hard it is to slide one plate across the other. That's the actual way of testing that. The units on it are kind of funny. Now we use viscosity because it indicates how hard it is to push a fluid, a lot of times like through a pipe or something, yeah.
You tested similar to friction?
Yeah, right. It's a little, the units are a little different because you're using shear stress and some other things. But yeah, it's a kind of a friction test. Yeah, it's kind of, I don't know, it's a little bit of a stretch, but it's kind of like the friction of a fluid in a way,
Right, okay.
So if you're trying to pump it, you want to know, what the viscosity is. Because the higher the viscosity, the harder it is to push it through a pipe. And then another thing we deal with is called vapor pressure. And these are all just some other miscellaneous fluid properties, okay? So vapor pressure is the pressure caused by evaporated water molecules. So the first thing is we have different kinds of fluids that we deal with. A liquid has what you call a free surface. So if you pour a liquid in a container, you get a surface of the liquid, whereas a gas or a vapor doesn't. You just got molecules floating around. And if you have molecules floating around, and if you were to put a sealed top on this thing, these things are moving fast, so they'll kind of bounce around. And some of them will bounce up against that lid, some of them won't. And they'll be going all over the place, you know. The ones that bounce off the top, they'll cause a pressure up here. Okay, and that's called the vapor pressure. And so what happens if you heat the water up? What happens to the vapor pressure, do you suppose? It goes higher, right? And it'll just keep going up and up until it hits the air pressure. If the vapor pressure and the air pressure are the same, there's nothing really holding the liquid in the container anymore. And what do you get when the vapor pressure heats up and reaches the air pressure?
Expands up.
Yeah, otherwise known as boiling, okay? So that's what happens. You know, when you heat up water, you just increase that vapor pressure until you hit the atmospheric pressure, and then the atmospheric pressure doesn't hold it in the container anymore. It just starts evaporating out. Okay? So those are just a couple of properties. We're going to use those when we look at pumping. So we just mention them now. Okay, so I've got a table in your book. I'm not sure which page it's on, but it's in chapter 1 at the end. 58, okay, thanks. It's on page 58. And what that has is what happens to water as the temperature goes up. Okay? So if you look at that, what happens is the temperature goes up is the density goes down, the vapor pressure goes up, and the viscosity goes down. Okay? So what do you think happens in the summertime? Is your water harder or easier to pump generally? Yeah, it gets a little easier because the viscosity goes down and the density goes down too. So it's a little bit easier to pump. Harder in the winter, easier in the summer. It's the general rule. Okay. And one other thing we've got here is the effects of pressure on water, or atmospheric pressure, actually. We'll kind of get to what atmospheric pressure is exactly here later, but another little effect that we deal with is atmospheric pressure in PSI. You know, the atmosphere exerts our pressure on water and on us and on everything. And it's just caused by the weight of the atmosphere above your head or above whatever the object is where the pressure is being exerted. As you go up, the atmospheric pressure drops, and that can affect some things as well. I used to live in Flagstaff, Arizona, and that was about 7,000 foot elevation. So the atmospheric pressure was quite a bit lower there. Remember, I had to get new jets for my carburetor because, you know, a lot of that stuff doesn't quite act the same when the atmospheric pressure changes. So, you know, that's something to be aware of. It affects pumping also. Those are just some things that primarily affect pumping, so we just look at them real quick here, just basic water properties, okay? All right, so that's chapter 1 there. Everybody good with that? The primary ideas in there is density and specific gravity. I mean, that's the primary thing we're looking at, okay? Okay, so due Wednesday, what is today? Is today the 29th, is it? Okay, so 30th is set, so 1, 2, 3, 4. So Wednesday the 4th, I think it is. How about doing 6.1 through 6.5? Okay, now, everybody finding those okay in your book? They're in the very back of the book. It's called Density Specific Gravity Worksheet. Yeah, it's 2 pages, 6.1 through 6.4 on one page, and then 6.5 is on the
And
next
you need
one.
that table of hydraulic properties for the last problem.
Yeah, you do, right, yeah.
Which is
What
in
page
chapter.
does it say on the book?
It isn't like a page, it's just towards the back of the book. The worksheets are listed in order, you know. Unfortunately, there are 2 sets of worksheets though. So, this is the ones in the back. What's that?
We get rid of this stuff.
Yeah, you could if you wanted to, yeah. It's just kind of for practice is why those are in there.
So everything in front of 6 point can take an applicant.
Yeah,
As
all
far as
those
worksheets.
yeah, they can all go.
There's just 1, 2, 3, 4, 5, 12.
Yes, yeah, and the fifth one's on that
Not binder, it's anything else.
Now, that fifth one's a little bit tricky, you know, and sometimes I give you a little bit trickier ones just for fun. Just one of them. Okay. Everybody finding that okay? A lot of them, the new ones.
I mean, I'm not.
Everybody all right? And then I call out that hydraulic properties table on page 58 that you're just looking at, okay? You need that for 6.5. Okay. Now we'll go over any questions you got on Monday. All right. All right, so that's the first general thing we're going to look at. Now, the next thing we're going to look at is pressure, okay? And this is an important property for fluids. So we'll start with, so this is, I don't know what page this is on, about 60 something. 59, oh, okay, 59. So 59, here we are. Okay, so a force is a push or a pull. So if you push on something or pull on something, you're exerting a force on it. All right, weight is a force that's caused by the pull of gravity. Okay, so weight is a force caused by the pull of gravity on an object. Now notice that the units of weight are also in pounds, okay, because force is measured in pounds and so is weight. Now what we have with pressure is we take the weight or the force and we divide it by the area over which it's exerted, okay. So pressure, the common units in the English system are pounds per square inch, PSI. Sometimes people get a little abbreviated with it and they call it pounds, but it's really pounds per square inch is what it is. Okay. And maybe to illustrate the difference between pressure and force, you know, let's look at what happens when somebody walks on the snow. Okay. You know, if you're walking around in deep snow with boots on, and let's say you're in a normal place that has snow as opposed to Oregon where the snow's a little light and fluffy as opposed to being like concrete before it sets. Let's say it's in the, kind of up north somewhere, lighter snow, you'll sink in, okay? Now, if you don't want to do that, you can come up with snowshoes, right? Now, snowshoes don't change your weight at all. They don't make any lighter. If anything, they make you just a little bit heavier. But what do snowshoes do? They spread it out, yeah, right, okay? So that's the difference there between force and pressure. Your weight is a force. It's just how hard you're being pushed down. But pressure is the force divided by the area. So that's why people wear snowshoes or cross-country skis or something like that, because it spreads the weight out. Okay? That's the idea of pressure. All right, so if you got a 72-pound force over 12 square inches, you know, it's pretty straight up. You just take the pressure, take the force divided by the area, and you get PSI. Okay.
What page is this problem on?
59.
59, yeah. Okay, so we'll just take the pressure over the area, and we'll have 72 pounds, and we'll just divide it by 12 inches squared, and work the numbers, and you get 6 pounds per square inch, okay? And that's about it. You just work with the numbers and get 6. Take 72 divided by 12, and the units are pounds per square inch. Now that's often abbreviated 6 pounds per square inch, PSI. Now let's have a look at water, because that's what we deal with a lot here. So let's say we've got water in a container. What causes the pressure is the weight of the water. Okay? So what we've got here, let's just take a kind of a tube that's a foot high by an inch by an inch. So let's figure out what the water would weigh in there. Okay? So what we've got is a foot times an inch times an inch. That's the volume of that thing. We want to get consistent units, so we want to take a foot by a 1/12 of a foot by a 1/12 of a foot, and that'll get us the volume, 0.006944 cubic feet. Okay? We're converting those inches into feet, so the units will match. So that comes out to be, you know, it's a pretty small number there, okay? So 0.006944 pounds per square inch, or excuse me, square feet. Cubic feet, okay? All right. So now we can figure out how much the water in that little container weighs, because we'll take the volume and we'll multiply that by the density of water. So every cubic foot of water weighs 62.4 pounds. So the water in that little tube is going to weigh 0.433 pounds. Okay. So we've got this water and it weighs 0.433 pounds. And then we've got the area on which it acts, which is an inch by an inch. That's a square inch. So if we take the weight, 0.433 pounds per square inch, pounds, and divide it by the area, 1 square inch, we get the pressure, 0.433 pounds per square inch. Okay? So that's the pressure at the bottom of that tube that's caused by the water. Everybody okay with that? Now let's start changing the tube a little bit. What if the tube is 2 feet high? What do you suppose the pressure would be? Yeah, I think that's a pretty good guess there. So it'd be twice 0.433. So if this is 2 feet high and an inch by an inch, the pressure would be twice that. So what we're seeing here is that the pressure depends on the height of the water to some degree, okay? And it's just a simple linear relationship. Higher the water is, the greater the pressure. All right, now what if we change the overall size of the tube? What if we don't make it taller, but we make the bottom of the tube bigger? Let's see what's going to happen. Okay. Now, if we go 2 inches by 3 inches instead of an inch by an inch, what happens here? We get 6 square inches at the bottom, don't we? So what we've done there, we've made that tube 6 times bigger because it's not 1 inch by 1 inch anymore, it's 2 inches by 3 inches. So instead of weighing 0.433 pounds, the water is 6 times as heavy, it's 2.3 pounds. 2.6 pounds, I'm sorry, 2.6. So now, instead of 0.433 pounds, we've got 2.66 pounds. No, we don't, we've got, I'm sorry, 2.6 pounds, there we go. So we got 2.6 pounds, 6 times the weight, pushing down on 6 square inches. Well, what happens there is you end up with the same pressure, okay? 0.433 pounds per square inch. Because we got 6 times as much weight, but it's pushing down on 6 times the area. Okay? So that gets you to a conclusion that's maybe a little different than what people might think, and that is that the area doesn't matter. All that matters is the height of the water. So if you're a foot below the surface of the water in a swimming pool or a foot below the surface of water in a big lake, it doesn't make any difference. You're going to have the same pressure. Okay? So what you have is just a simple relationship between depth and pressure. And the key number there is 0.433 pounds per square inch. Every foot of water will get you 0.433 pounds per square inch. And it doesn't really matter what the size, or as it turns out, even shape of the container is. It just has to do with depth. So all you have to do to get pressure is take whatever the depth is times 0.433. That's all there is to it. And you should never make it more complicated than that. And my experience with this stuff is when people have trouble with it is when they make it too complicated. They try and make it more than that. So to find pressure underwater, regardless of the shape or size of the container, so it'd be the same for any of those containers, it would just be 0.433 times the depth. That's it. Okay. We good with that? Any questions?
If it was something that was like a foot long and it was a foot deep, would you take the average of all the pressures of that foot object? If it was like a door on a dam or whatever, and it was 20 feet down, how much pressure is on the whole door? You would take an average of.
Well, it wouldn't be how much, if you want to look at the force on the door. Now, pressure is more like an instantaneous thing at a point. So you would look at the average pressure pretty much. But you have to worry a little bit about the shape also. So it gets a little tricky. But
Jumping ahead a little bit.
yeah, but what you're saying essentially is right, yeah. Right. Okay. Okay, so what's the pressure at the bottom of a 30-foot deep tank of water and 30 feet below the surface of a lake? So what's that pressure going to be? Is it? Okay. Yeah, about 13? Yeah. All right. So again, don't make this harder than it is. It's really straight up finding pressures. Yeah, there's a few little things like what you were just saying there about varying pressures at different depths you have to consider, but when we get deeper into this, but pressure at a certain depth is straight up, and don't make it any harder than it needs to be. So 30 feet times 0.433. Now I use PSI here just to keep the units simple, per foot. Okay. And if you take it all the way out, that's 12.99 PSI, which means pounds per square inch. If you called it 13 PSI, I think we'd be good. Okay. We could round that. Okay. You okay with that? Okay. And that's all there is to it, okay? Okay. Now, on the next page, I've got a number of situations there where I'm showing a little pressure gauge. That little symbol means a pressure gauge. So I've got 12 feet under the surface of just a simple water tank. I've got 12 feet under the surface of those other two rather more complicated water tanks and how they're shaped. Got pressure gauges there and there and there. I've got it 12 feet down in an 18-foot deep water tank. I've got 12 feet down in front of a dam holding back a reservoir. I've got a retaining wall with soil that allows the water to flow through the soil. I've got a tank and a pipe 12 feet down, and I got a curvy tank. What would be the pressure in each of those gauges? Yeah. Okay. Now that's a little bit odd, but it's true. They're all the same. Okay. It doesn't make any difference as long as you've got connected water. That's a given depth. It's just 12 times 0.433. That's it. Okay. If you ever, the one thing I've noticed here is on retaining walls. They got to be a little careful here because you get all this pressure building up behind a retaining wall. It can just push the wall over sometimes. If you look close at those things at the bottom, what they'll do, they'll put in little 4-inch or I think about 4-inch, maybe less, PVC tubes that run through the retaining wall. They put some filter fabric on the dirt side to keep the stuff from washing through, and they just let that water seep out from behind that thing because they don't want the water building up behind the retaining wall. It builds pressure up, and that can end up really pushing hard on the wall. So it's, they can handle the dirt stacked up behind it, but the water can really add a lot of pressure. Yeah.
So the pressure, you always use inches for pressure.
PSI, yeah, pounds per square inch, right? That's normally how gauges read, and that's just how
So
we
if
read
this
it.
was, let's say, if this was 3 foot high,
Yeah.
you would just take 12 times 3.
No, because the conversion handles all that for you. The conversion goes from feet to PSI directly.
Yeah.
So you don't have to change the feet into inches. Foot times 0.433 will get you the number in PSI. That 0.433 takes care of all the unit changes you need to concern yourself with. It does it for you. Okay, so just height in foot times 0.433 gets you PSI. Just that simple. Okay. Okay, and that number should be on your formula sheet too. It's a real common number in hydraulic. It's on the, so that number is on the left-hand side in the middle there. Foot of water is 0.433 PSI.
Now this is just because of gravity.
Yeah, weight and gravity.
Yeah, the weight and gravity, and so no matter the area on the bottom,
Right,
if the height is still the same, then
you're done, yeah. If the height, it's just height, that's all it is. Nothing else matters. Even if the tank is curved, even if the tank is shaped weird, whatever, how big the tank is, none of that makes any difference.
okay.
Just height, gets you pressure. That's simple. Okay. Temperature matters, yeah. The hotter it is, the less the density, the less the pressure. But it doesn't vary real dramatically, so people usually just use 62.4, which is, I think, one of the heavier cases, and they just call it good. They don't get too,
Yeah, like I said, 60 degrees or something.
Yeah, it's some standard temperature. But you could, if you get up to like 150 or something, it's not that much different where it would make a huge difference in pressure. Okay. This is a water tank in Salem. Yeah, actually it's Kaiser, yeah, right up there. What's the pressure? If that thing's 100 feet high, yeah, right. It's just pretty straight up. Now, this is a very common type of water tank. If you ever drive I-80, you'll see one of these in every town because the ground's really flat, in the Great Plains when you get out in Nebraska and all that. You'll see these water tanks all over the place. They usually put the town name up there, kind of, looks good and all that. Yeah, right. That's a Kaiser actually, but, well, okay, Salem Kaiser. Now, think about, why they're doing it this way, because what water plants like to do is water plant operators get up early in the morning quite often, and they go and they start making water. This is especially the case in Corvallis, like the later they get in the summer, the earlier the water plant operators get because they need more water in the early. They'll start coming in at like 3:30 in the morning in the height of the summer. And they got pipes under here. And what they do is early in the morning, before most people are up, and also when the power is nice and cheap, because you get varying rates on power for industrial usage. If you use it at night when there's not a lot of demand on the system, you get it cheaper than if you use it during the day. They'll go there and they'll make their water at the plant, and then they'll pump it into this tank. Now notice how they built the tank. Tank doesn't go up or down a whole lot. It's just right in that one area. Okay, so they'll fill that tank. During the day, the tank will drain down as people use the water. But what happens is that height doesn't change a whole lot. So they put that tank up high on purpose on like a stand of some type. And what they figure out is, okay, we want a certain range of pressure for our system. Normal water pressures might go from 20 to maybe 60 psi, something like that. So they'll figure out for this surrounding area that this tank feeds, okay, we want, let's say this tank goes from, let's say it goes from 120 to 80. What's the range of pressure they get out of that tank? If it's, instead of being the straight simple 100 that I gave you, what if it varies from 80 feet when it's drained down low to 120 feet? What's the range of pressure you'll get around that tank? Yeah, it'd be, I'm not sure, let's see what we got. So we got 120. So that's about, excuse me, about 52 psi here. Something like that. Okay. So they do that on purpose, and they plan that out, they're looking for a certain range of pressure, so they'll have the tank, high will be the upper range and low will be the bottom range. Okay. Now, if you're, if like Albany, they've got a tank up in North Albany, where it's nice because they've got a hill out there. They don't have to put the stand in there, which is kind of expensive. They can just build a flat tank up on a hill too. It's cheaper, of course. Okay. Now, how about a tank like that? That's on, I think it's Waverly, or is it Waverly? I think that's in Albany there. How do they do that? See, the advantage of this elevation is you're getting this nice consistent pressure on your system. You pump the water up in the morning when the power is cheap, and when you're making the water, you just let it sit there during the day, and you don't have to do anything. It's just sitting in there, nice cushion of pressure, pushing down. See, it's a nice system, very even pressure. How's this one going to work? Okay, and what do you got there to keep that nice pressure? That pressure lid? You need more than that. That's not a pressure tank. That'd be a heck of a big pressure tank. But what do you got? No, it's more because when you draw this thing down, you're going to run out of pressure. See? Yeah. Yeah, and if they need more than 8 pounds, so what does this got to have with it? It's a pump station, yeah. Okay, and they got valves that'll read the pressure in the system and send a signal to the pump to come on when the pressure drops below a certain level. Okay, kind of like you would in a well or something like that. Okay. All right, so that's different kinds of tanks. And actually, city of Corvallis, I think they've got 3 different zones, and they've got tanks up on hills. They've got the city divided. I think it's 3 different zones of pressure. You don't want to go much above 60 psi. You'll start blowing dishes out of people's hands or something when they turn on their water. You've got to put pressure reducing valves or something. But you don't want that high of pressure in your mains here. You want to keep the pressure a little in a good range, but not too high in the main. And y'all know the minimum pressure for a distribution system? 20 psi. I mean, what's that? They'll go to 20. They'll pull down to 20. Now they like it higher. I mean, 20 is the lower threshold. But like if, I spent some time with the City of Albany water distribution system, and if a customer calls them and says, hey, my pressure's low, they'll come to the meter. The meter's the boundary between the public side and the private side. They'll pull the meter, put a pressure gauge on there, test the pressure. If it's 20 PSI or lower, they tell them to call a plumber. That means the problem's on the private side. If it's above 20 PSI, or excuse me, hang on, no. If it's 20 or lower, they'll fix it, okay? If it's 20 or higher, they'll tell the customer to call a plumber. Now, the other thing that Albany does that I think is smart is they don't mess around fixing water services. You got any problem with the water service going from the main to the meter, they just pull the water service out and replace it. Because they figure if they fix some little problem, they'll be back next year fixing some other little problem. So don't mess with it. Just pull it out and fix it. Just replace it. That's what they do. Okay. All right. What if we got a fluid other than water? Yeah, what we're going to do, we're going to factor it up or down by the specific gravity. So that's one reason why they give you that specific gravity, the use of it. So if you have a fluid other than water, you just take whatever the height is times the 0.433 psi per foot times whatever your specific gravity is, because that's just a ratio. Okay? So what if we got a tank of oil has a specific gravity of 0.92? What's the pressure at the bottom of that? Oh, okay. Yeah, so we got 30 feet and specific gravity is 0.92, I think. Sounds about right. Everybody doing all right with that one? Pretty quick. You just do the regular pressure calculation and you multiply by 1.5 like that. Or 0.92. You okay with that, 11.95? Any questions on that? All right, so that's just a bit on pressure there. Doing all right? You got any questions on that? Okay, so for Wednesday, we do 6.1 through 6.5. When I just go into Moodle for a second just to show you what that looks like. So
You want us to turn a paper copy, right?
of 6.1, you can just do it right on that worksheet.
Right. I didn't know if Moodle was on Moodle.
Oh, all I got on Moodle, I just list the homework and stuff. That's all I wanted to show you. So in Moodle here, this is my hydraulics class in Moodle. I've got a homework list. So here's the homework. This is just ignore everything below the line. So what I'll do, I'll move this up above the line here today sometime. So that'll be on the homework list. So if you need to know what the homework is, it'll be in Moodle. Now what I've got here, I've got the answers for a lot of the questions. Number 5, I won't give you the answer for. I'll let you think on that one a little bit. But the others I give you answers for if you want to check. Now keep in mind, if you're just a little bit off of mine, it's probably just rounding error. Don't get worried about that. General rule is if you're within 1% of what I got, it's probably we just rounded differently. It's not a big deal, okay? Now the other thing I've got in here are recordings. So there's the recording from Wednesday. You click on that, you'll just go out to YouTube. And I've got the recording of the lectures there, okay? So that's available too. All right, so we're doing all right? So we'll go over the homework. If you've got questions, I'll take them on Monday. All right? You good? Good, all right? Okay. All right, I hope you all have a good weekend.